our speaker today. Cecilia got her PhD from the Federal University of Rio de Janeiro at Brazil in 2014. And then she worked as a postdoc at Texas A&M, Brown University, and Tulane University. She's now an assistant professor at Drexel University. And Cecilia's research interests cover PDE, fluid dynamics, stochastic process, and data simulation. So today she will give us a talk for rates of convergence to statistical equilibrium, a general approach and applications.
Yeah. Thanks, Nan. Thanks for the invitation. And so thanks for the opportunity to speak here today. So let me just give a brief outline of my talk. So first of all, this is based on joint works with Nathan Gladholz, where I did a postdoc at Tulane University, but it's also been a very intense part of my research lately related to this stochastic fluid flows. So more generally, my talk is going to be about physical systems that are subject to some kind of randomness. And what I'm mostly interested in studying the statistical equilibrium of such systems. And what I'm going to do is to present a general approach for showing rates of convergence towards the statistical equilibrium of such systems. And then I'm going to show two applications of this general approach. The first one will be in how to approximate the statistical equilibrium or the invariant measure of 2D stochastic Navier-Stokes equations through the statistics of some numerical approximations. And the second application, I will show how to obtain rates of convergence to the posterior measure in the context of Bayesian approach to inverse PDE problems. Okay, so just as a brief motivation, let me just say how randomness naturally appears in physical systems. So say you have a certain state variable U that is modeled by an evolution equation of this form. And then randomness can appear in this system in several different ways. For example, if you want to obtain the prediction of the state variable U at a future time capital T by using your model, but say you don't have complete information about where your system started, so you have some uncertainty in the initial data, so that will be represented by a certain random term eta here. So that will be a source of randomness in your system. Or in the context of a filtering approach, for example, when you're trying to obtain predictions about the state U based on observations of U, say Y, given through an observation operator G, then you also have to take into account the observations are naturally subject to error eta, which will be then another source of randomness in your system. Or uncertainty can be actually can appear in the model itself, for example, due to simplifications that are done in the derivation of the model. And then in order to account for this uncertainty in the model, it's common to introduce a stochastic forcing term in the equation. So for example, in the context of geophysical fluid flows, one usually uses the stochastic forcing terms in order to account for small scale processes such as radiation, clouds, and so on that are usually left out of the derivation of such geophysical models. So these are just several examples just to show how randomness naturally appears in the modeling of physical systems. And really what we want to do is how to be able to extract information about systems that have this random character. So here I'm just putting this very simple example of, say, Lorentz 63, which is the time model for turbulent flows. And then if you pick an initial condition, and for each initial condition you draw what's the trajectory of Lorentz 63. I picked here several random initial conditions, and for each one I have a different color here representing the different trajectory. And you see that each one, of course, they have this erratic behavior in time. But if you look at the ensemble average over all of these trajectories of the norm of the solution, which is just a three-dimensional vector here, then you obtain this black curve here that is a lot more well-behaved, right? So that's just giving a simple argument for why looking at averages of physical quantities is a natural approach when you're dealing with physical systems that are subject to randomness, right? And more than that, this example is also telling you that in order to extract some useful information, you probably also want to wait long enough so that the system, this average has somehow stabilized, right? So that indicates that some useful information about the system would be obtained under the state of statistical equilibrium, which you can define as the state of a closed statistical system in which the average values of all the physical quantities characterizing the state are independent of time. So this is just defining what this is in words, but let me try to give a more, let me try to put these words into mathematical terminology. So for example, if for each time t, I introduce this map pt, that for each initial condition u0 and set A gives me the probability that the solution starting from u0 at time t is going to belong to the set A. Right, so this is essentially giving me the distribution of states that started from this point at time t, right? Of all possible states that started from that initial condition. So with this terminology, we define a statistical equilibrium for this system by a measure mu star that is invariant under the action of this map pt, right? So such that pt mu star is equal to mu star for every t. So that, which is essentially saying the distribution of states under this measure is constant in time, right? So just to be clear here, when I write this pt, the action of this map pt on the measure mu star is also a measure that is defined in this form here. So pt mu star for any set A is the integral of pt u0, with e0 being integrated with respect to mu star. Okay. So, okay, so this is how we define statistical equilibrium. And as I said, our goal is to obtain information about the random physical system under the state of statistical equilibrium, or more specifically, to obtain averages of certain observables phi. Can you see me changing?
Sorry, changing what?
Because I just changed the slide, but it didn't change on the screen.
Oh, no,
so
it's
I'm just
not
wondering
for
if
us. We're still at the statistical equilibrium screen.
Okay, let me stop sharing and share again. Okay, so you should be able to see this now, and it should be changing. Right, so the goal is to obtain information about that system subject to randomness under the states of statistical equilibrium, and more specifically to obtain averages of observables, say phi, with respect to mu star, with respect to the invariant measure mu star. But of course, in practice, you cannot compute this average or this integral exactly. So what you do is try to approximate it. So what you want is an efficient method of approximating this integral. So what's the natural thing to do? Well, suppose you have, you're able to generate a certain sequence of states, say U1 to Uj, and then natural thing to do is to take the average of this observable phi over the states, right? And then to hope that as you take the number of such states to infinity, that this sum is going to converge to your desired integral, which is going to help provided your system has useful ergodic properties. Okay, so just to give an example of an observable phi, just to make things more concrete, if u is the velocity field of a fluid flow, and phi of u is the altitude norm square in space, then the integral of phi with respect to the invariant measure mu star would represent the average kinetic energy of the fluid flow. So that would be the quantity that you're trying to approximate. Right, so under this setting, of course, there are some natural questions that arise. The first of them is, can you actually show that existence, oops, I don't know why I went all the way to the beginning. can you actually show existence and uniqueness of, and it froze again, right?
Yeah, I think it's frozen again.
Yeah. I think I had my computer connected to too many things, so I'm trying to disconnect just some things, and hopefully it's going to help now.
Can I ask a quick question while you're maybe doing this? Am I right? So this is the is everything time independent here in the sense as the invariant measure actually?
The invariant measure is time independent, yes, by definition, yes.
But what happens if you have a non-autonomous flow, like if you have an advecting velocity field or something, which is?
Oh, no, the flow can still, the flow is not stationary.
Okay.
But it's the measure that is stationary under the action of the flow. Okay. Right, so it's not evolving in time. It continues as the same. The distribution does not change in time, okay. Which is something that you can only reach, in a state of statistical equilibrium after the system has settled into this equilibrium. So you just imagine like everything is chaotic, but after a very long time, so in the long time behavior, things are settled down into one distribution that now is not evolving anymore.
Okay.
So that is just the big picture.
Okay, thanks.
All right, so the natural question is, can you show existence and uniqueness of this measure mu star, this invariant measure mu star? And more than that, can you also show how fast this convergence is happening, right? So say for a given error epsilon, how many states do I need so that the sum is close to my desired integral within an error epsilon? And this is precisely the kind of question that I'm more interested in obtaining explicit convergence rates in this approximation here. And so the approach that I'm going to show now is precisely in order to address this question of convergence rates in this approximation, which is actually going to also include an answer for uniqueness of the invariant measure. Okay, so let me try to describe in a very general way what's this approach, and then what we're going to do is to apply this to the two applications that I have later. So I'm going to denote the phase space associated to the physical system to be, I'm going to denote that by X. So for the applications, we're interested in the case where X is infinite dimensional. So think about X being the phase space of a PDE, being, for example, the space of square integrable functions in space and time, right? And then that map P that I defined before, which was giving me the distribution of states, we're going to define that in a more rigorous way to be a Markov kernel associated to this physical system, okay, which is rigorously defined as a map on the phase space X cross the sigma algebra of Borel sets in X. So I'm thinking of X at least as a topological space with values in the interval from 0 to 1 that satisfies these two properties here. So the first one is if you fix a set A in the second component, then this is a measurable function in X. And the second one is that if you fix a mu, then this is going to be a probability measure in the phase space, okay? So think about the first component being the initial condition and the second component being the set where you want to see if your states are reaching after a certain time t. And then I'm going to denote the invariant, I'm going to consider an invariant measure mu star that is invariant with respect to this Markov kernel P, okay, so such that P mu star is equal to mu star. And our goal is to approximate this integral, right, for observables phi. And then I said before, well, the natural way to approximate this is by using those sums, but I didn't tell you how to generate those states uj that are going to use in this approximating sum. So the natural way to obtaining this is to draw them from the measures that are iterations through the Markov kernel from a certain initial distribution mu0. So say you start from a distribution mu0, You can draw an initial point from that. Then when you consider P of mu0, that's a new measure. And then you can draw a point U1 from that. And then P squared of mu0 is going to be a new measure that you can draw a new point. And then from these iterations, you can construct a sequence of points that you can use to construct this approximating sum. Okay, and the question is, again, if this is effectively going to converge to this as the number of points goes to infinity. But written in the setting where the states are generated from iterations of the Markov kernel P, answering the question of this convergence can be done by answering whether these measures here, which are the iterations of P, converge to the invariant measure mu star. So in other words, really what we want to do is to show that P and mu0, these measures, converge to the invariant measure mu star as the number of iterations goes to infinity in a certain distance in the space of probability measures. Okay. So it turns out that because we are interested in the case where X is infinite dimensional, distance in the space of probability measures that is going to be suitable for us is this Wasserstein distance, which is defined as follows. So suppose you have a distance function rho in the phase space, so on X cross X. Then you define the Wasserstein distance with respect to this rho between any two measures mu1 and mu2 to be the infimum over all possible couplings of mu1 and mu2, or joint distributions of mu1 and mu2, of the integral of the distance function rho with respect to this coupling. Okay, so take this integral and then take the infimum of this over all possible joint distributions of mu1 and mu2. That's your Wasserstein distance. So we're going to try to obtain this convergence with respect to this notion of distance. Okay. And the main tool in our approach is this Wick-Harris theorem that was proved by Ehrer, Madelin, and Schweitzer in 2011, which gives general conditions that the Markov kernel P has to satisfy so that you're able to show an inequality of this form in the Wasserstein distance for some distance function rho twiddle in the phase space. So essentially, an inequality of this form is called a spectral gap inequality for this Markov kernel P. And it's essentially given as exponential convergence between iterations of P starting from any two measures mu1 and mu2. And why is this going to answer the question that we wanted, which is convergence towards the invariant measure? Because if you take mu2, for example, to be the invariant measure, mu star, then of course, Pn of mu star is going to be equal to mu star by invariance. So if you just plug this here and take mu1 to be your initial distribution, mu0, then this spectral gap inequality is going to precisely give us exponential convergence of P and mu0 towards mu star in this Wasserstein distance. So essentially, our job in the applications will be to verify that the assumptions in the Wick-Harris theorem are satisfied so that we are able to show this convergence. So let me say, what are these assumptions? It's essentially three main ingredients. The first of them is that there exists a Lyapunov function for this Markov kernel P. So a function V for which the action of Pn on V is less than or equal to an exponentially decaying term plus a constant. Okay, so this action is decaying exponentially up to a constant. The second one is this rho contractivity property that says that for some distance function rho in the phase space, you are able to show that if any 2 points are close to each other, in the sense that rho uv is less than 1, then the distance, the Wasserstein distance between these processes starting from u and v contracts. Okay, so this alpha here will be a constant less than 1. And the third property is rho smallness that says that if u and v are in some level set of v of the Lyapunov function v, then the distance between the two processes is bounded by a constant that is less than 1. So essentially, the proof of the weak-Harris theorem under these assumptions goes more or less like this. So you essentially divide the proof into 3 cases. So first of all, you notice that in order to show the spectral gap inequality for any 2 measures mu1 and mu2, you first notice that it's enough to show for the case where mu1 and mu2 are both directs. So say concentrated at U and V, okay? So it's enough to show this 4 points. And then you divide into 3 cases. First one, if these 2 points are close to each other, in this sense here, where you use the contractivity property to bring these 2 processes together. Second case is if U and V, okay, maybe they are not close to each other, but they are in a level set of the Lyapunov function, then you use the smallness condition. And then the third situation is if they are not close to each other, not in a level set, then all you have to do is to rely on the Lyapunov function to bring these processes together. So you rely on this exponential decaying property of the Lyapunov function so that you obtain, so that you're able to obtain this decay here in the Wasserstein distance. Okay. So provided you're able to satisfy all of these conditions, then you conclude the spectral gap inequality for a distance rho twiddle that is not exactly the same rho from the hypothesis, but it's rather a distance that is weighted by the Lyapunov function, right? So this is reflecting the fact that we are using the Lyapunov function to obtain this contraction. So in order to obtain the existence of the Lyapunov function, that is not going to be too hard, especially if you're dealing with dissipative dynamical, dissipative physical systems, where you can rely on this dissipation to obtain this Lyapunov function. But for the other 2 properties, the contractivity and smallness, that's where we use this technique called the asymptotic coupling technique, which is essentially relies on constructing a modified kernel P twiddle that whose underlying process is going to converge to the original one, almost surely pointwise. So typically you define this P twiddle through a control argument, right? So that you can obtain this contraction. And then in order to obtain the smallness and contractivity properties, you essentially apply a triangle inequality by putting this modified kernel in the middle. And then the estimate of the first term would follow precisely by contraction, provided you choose your control well. In the estimate of the second term would essentially, this is what we call the cost of control term that has to be estimated. Okay. So this is a general approach. Now let me go to the applications where we try to verify that these properties, that these assumptions of the weak-Harris theorem are satisfied in some particular scenarios. So let me talk about the 2D stochastic Navier-Stokes equations first. So I'm going to consider 2D stochastic Navier-Stokes equations in the vorticity formulation. So C here is the vorticity field, the random vorticity field, use the velocity related to C through the Biot-Savart law. And here my stochastic forcing term is going to be wide in time and frequency localized in space, which means that I'm only forcing a fixed finite number of directions in space, but I am in the situation where I consider that I need a large enough number of directions in space to be forced, okay? This WKs here are just a sequence of independent real value Brownian motions, and the sigma Ks are precisely representing the directions in the phase space where I'm putting stochastic forcing term. And then I'm considering periodic boundary conditions so that the natural phase space is given by the space of L2 functions on my periodic box with the 0 spatial average condition. So my goal is to try to approximate mu star here for us is going to be the invariant measure associated to this stochastic system. And I'm going to try to approximate this by using the kernel associated to a certain numerical discretization of that equation. So the discretization that we consider is semi-implicit in time scheme and spectral Galerkin space. Okay, so that you end up with the discretization here. This pi n is just the the Galerkin projection onto a finite number of modes in space. Delta is the time step, okay? And then essentially, again, I want to approximate this integral here where mu star is the invariant measure for the original system for some observable phi by using the iterations of the kernel associated to this discretization, starting from some initial measure mu0. And again, I'm going to analyze this convergence by analyzing the convergence of these measures towards the invariant measure mu star. With respect to that Wasserstein distance in a certain distance world twiddle in the phase space. So in order for us to be able to apply the Wick-Harris theorem here, first what we have to do is to apply a triangle inequality for this term here. So essentially, I'm going to put first in the middle the discrete kernel applied to the invariant measure of the discrete system that I'm denoting by mu d star. And then secondly, I'm going to put the continuous kernel, the kernel associated to the continuous system, applied to the discrete invariant measure. So then in the end, you end up with these three terms here. And then what I want to point out is that in the first one, you have the same kernel, but different measures. Same for the last one, you have the same kernel, but different measures. But here you have the continuous kernel, whereas in the first one, you have the discrete one. So essentially, in order to estimate this first term here, all I have to do is to obtain a spectral gap inequality for the discrete kernel. In order to estimate the last one, I need a spectral gap inequality for the continuous kernel. Now, for the middle term, I have same measure, but different kernels. So essentially, to estimate this, I'm going to have to obtain the numerical error estimates between the discrete solutions and the continuous one. Okay. All right, so this is what we're going to apply the Wick-Harris theorem to obtain the spectral gap for this term and then the last term as well. So let me just go briefly how you verified that for the first term. So in this case, we can show that V of u given as an exponential of gamma u squared, where this is the norm in L2, for a parameter gamma that is sufficiently small, this is going to be a Lyapunov function for the system in the sense that I defined before. Then we're going to consider a distance in the phase space that is the minimum between 1 and the distance between u and v divided by epsilon. This epsilon here is essentially giving us the spatial scale that we need. It's essentially characterizing how small is small. So the scale where we are able to obtain contraction, okay, for the world contractivity property. All right, so we can show that indeed this v is the Lyapunov function for the discrete kernel PD, and it actually satisfies a stronger form of the Lyapunov inequality of this form, so with no constant here. And then, so this takes care of the Lyapunov part, but then remember we need the contractivity and the smallness part for the Wick-Harris theorem, and that's where we have to construct that modified kernel P twiddle, right? That I said it's usually controlled, it's usually constructed with a control type argument. And that's exactly what we're going to do. We're going to take our original discretization and then introduce a control term in the equation, which is only controlling a finite number of Fourier modes, but then because of dissipativity, you're able to control the smaller scales as well. And then, so provided you have enough number of modes being forced here, you're able to show that this modified process converges to the original one almost surely pointwise. And then in order to do that triangle inequality kind of argument to be able to obtain the contractivity and smallness properties, what we're going to do is essentially to see the solution to this modified system that I'm calling C twiddle in two ways. So first of them, you can see this as a solution to an equation that is a modified equation, right? That is because of this new term here in the equation, right? and corresponding to the noise W. Or you can also see Cecilia as a solution of the original equation, the exact same discretization that I had before, but with a different forcing term. So essentially, how if you absorb this control term, this new term into the noise term, then essentially this will be then a solution of the original discretization, but then just with a different forcing term that you can write as this W hat here, okay, with this CJ essentially being the control term. So under these two different ways, you can estimate that distance between any iterations, of the discrete Markov kernel starting from any 2 points C0 and C0 twiddle by using the triangle inequality argument, where this first term here you can estimate by using the contraction that you can show thanks to the control term. And the second term is, as I said, is going to be the cost of control term, that is precisely the price you're paying for introducing this modification into the system. But this you can estimate by the total variation between these two processes, which is it was essentially going to be estimated by the total variation distance between the laws of the law of the shifted process, the law of the shifted forcing term, and the law of the original term. Okay, and estimates of this form are usually you'll obtain by using Gershonov's theorem. Okay. So what I didn't say is that, of course, in order to obtain the contraction here that is going to allow you to estimate the first term, you're going to have to assume that the number of modes in the control term is sufficiently large. And this is how large you would have to be. All right, so with all of those, with that framework, you will be able to apply the Weak-Harris theorem and then in the end obtain the spectral gap inequality for the discrete kernel. So this would allow you to estimate the first term in that triangle inequality that had 3 times. For the last one, which will be a spectral gap inequality for the continuous kernel, will be the estimate would follow similarly, so with similar arguments. And then for the middle one, where you have to estimate the term that had different kernels, then essentially, I'm not going to go over the details, but just by using the definition of the distance row twiddle, you would see that this can be estimated by an integral with this integrand, where you end up with these exponential functions here that come from the definition of the Lyapunov function. So you have to estimate this by obtaining exponential moment bounds for your system. And then this expected value here, notice that we're going to have to estimate precisely the difference between the original solution and the numerical approximation of that solution. And that's where the numerical error is going to appear. So let me skip these details and say what's the theorem that we get in the end is that if you start with an initial distribution mu0 that has enough regularity, which means that this integral here is finite for this exponential function, then you can show that there exists epsilon and gamma, which are parameters in the definition of the distance and of the Lyapunov function, such that if you define row twiddle, this distance in the phase space in this form, then you obtain this estimate for the Wasserstein distance between the iterations of the discrete kernel starting from this measure mu0 and the invariant measure of the continuous system mu star. So you notice that you obtain this exponentially decaying term here, and then the second term, which is precisely the numerical error term that depends on the time step and also the number of modes in the Galerkian approximation. One detail here is that I had this constant here, which is growing exponentially in time with the integration time, but actually we have some updates that are not out yet that we can actually obtain this estimate uniformly in time, but it's still work in the progress. So I just wanted to say that. All right, so in the few minutes that I have, let me just go over the second application which is in this context of inverse PDE problems by using the Bayesian approach, which is something that my research has been a lot more focused in lately. So essentially, what is this Bayesian approach to inverse PDE problems? The idea is the following: you want to obtain information about a certain state variable Q of a certain physical system by using observations of Q that are given through an observation operator G that depend on Q through an observation operator G and are corrupted by a noise term. And then the idea is that assuming a certain distribution for this noise, call it gamma 0, and assuming a prior distribution on Q, you want to obtain the probability of Q given the observations Y, which is the best estimate that you have for Q given the observations, by using Bayes' theorem, essentially, which you can write in this measure theoretical way in this form. So essentially what we want to do here is to approximate this measure mu that is called the posterior measure, and it's representing the probability of Q given Y. And it's given by an exponential of minus phi, where phi is what's called the potential, it's called a potential function, or also a negative log likelihood, and mu 0 is the prior distribution, and the z here is just a normalization constant. So the goal here would be to obtain a Markov kernel for which this measure is going to be the invariant measure, and then use that approach that I have using the Wick-Harris theorem to obtain convergence rates towards this posterior measure, okay, which is the quantity of interest in this framework. So just to give an example of a specific inverse PDE problem, you can think about trying to recover an incompressible velocity field Q, given observations of a certain passive scalar that is advected by this velocity field, right? So think about dye that is diluted in a fluid, and then you have observations about the concentration of dye, and then you like to recover what is the velocity field that is advecting that dye. So that's one example. And so let me focus here on trying to obtain those convergence rates. Again, the goal here is to obtain integrals of observables phi with respect to the posterior measure mu. So essentially what you want is to have an efficient way of computing these integrals, which in most applications of interest would be an integral over high dimensional space. And then by using that approach, remember what I want you is to construct that Markov kernel P that is going to hold mu as an invariant measure. And one way of doing this is precisely by using this Markov chain Monte Carlo methods that rely on constructing such Markov kernel P. And then once you construct that, you draw points from iterations of this kernel so that you can construct that approximating sum and then hope that you can obtain this convergence, right? So the difference between MCMC methods is precisely how to construct this Markov kernel P. Okay, there are several different MCMC methods, but the one that I'm mostly focusing on is this one called Hamiltonian Monte Carlo method. Okay, so briefly, one of the reasons why we're interested in HMC is because it uses Hamiltonian dynamics to essentially explore the parameter space in a more efficient way if you compare, for example, to random walk type methods. And why in infinite dimensions? One, because we are interested in applications where this space is infinite dimensional, such as in PDEs, but also because if we are able to work with MCMC methods that are well defined in infinite dimensions, then this is going to guarantee that the rates of convergence that we obtain are going to be robust with respect to any finite dimensional approximation, so that you would beat the curse of dimensionality. Okay, so that's why we're focusing on this framework. So just a bit of literature, in the HMC method in infinite dimensions was first defined in this paper by Vasquez et al. In 2011, where they constructed the algorithm and verified that it had the properties that are usually required in this kind of methods. But then ergodicity or convergence results for this infinite dimensional HMC method was only recently proved in this paper that first appeared in 2020. And essentially what we have is another way of obtaining this convergence result by using this weak-Harris approach, okay? So let me just go briefly over what the infinite dimensional Hamiltonian Monte Carlo method is. The idea is, assuming that your phase space X is an infinite dimensional Hilbert space, and assuming that your prior distribution is a Gaussian centered at 0 with covariance C, what you want is to construct a Hamiltonian system for which that is associated to a Hamiltonian function H that you assume to be with the potential part U and a kinetic part V. And then the idea is that you define the potential part of the Hamiltonian in such a way that when you consider this measure here, exponential of minus the Hamiltonian, which is a measure on the extended phase space, H cross H, and then you take the marginal of this onto the Q space, then you obtain precisely your posterior distribution, which is the one you're trying to approximate. So it's essentially relying on an extension of the phase space, constructing a Hamiltonian dynamics on this extended phase space, and then using the fact that the Hamiltonian is preserved by the Hamiltonian dynamics to then conclude that when you take the marginal of this extended phase space measure, you obtain the original, the measure you're trying to approximate, that because of this invariance this extended phase space measure is going to imply that this is also going to be preserved. So it's also going to be invariant. So this is the main idea behind the approach. So the Markov kernel here, assuming that you can integrate the Hamiltonian dynamics exactly, then you can just construct the Markov kernel to be the transition kernel associated to the dynamics of the Q variable in the Hamiltonian dynamics, right? So the probability that the position starting from a certain initial condition Q0 and V0, where V0 is drawn from the prior, probability that this is going to belong to the set A. That's how you define the Markov kernel. And then this P is going to hold the posterior measure as invariant because of what I said. And this is how the algorithm goes. It's starting from a certain initial condition Q0, you draw velocity from the prior, you feed that into the dynamics, and then you run that dynamics for a certain fixed integration time, capital T. And then at the end of the integration time, you discard velocity, keep the position, and that's what's going to be the next point in your chain. And then you proceed on constructing this. So in order to verify, in order to obtain the convergence towards the posterior measure, we want to, again, apply the weak-Harris theorem. For that, we are going to need to assume some conditions over the potential function phi that is that defines the posterior measure of mu. We need it to be uniformly, that the second for sure derivative of phi to be uniformly bounded. And we also need the second condition here, which is essentially a coercivity property for the for sure derivative that is going to essentially guarantee that we are able to obtain the Lyapunov function. So it's going to give us the dissipativity that we need to obtain the Lyapunov function, together with the smallness condition on the integration time. So we can prove that you have a Lyapunov function that is given either by a square of a norm or in exponential form. So series phi is a Lyapunov inequality. And then now remember that for the contractivity and smallness, the usual approach is to define that modified kernel. I think it froze again. So in order to define that modified kernel, so essentially what you want is you start from any 2 points, Q0 and Q0 twiddle. And then say you drew a velocity for this point here, V0. And then after integration time T, right, you end up at a point here. So the question is how to define, remember that the p-twiddle has to be defined in a way that the associated process is converging to this one almost surely point ones. So the question is essentially how to define a velocity for this one so that after you evolve this for integration time t, this is going to approximate the other trajectory. Okay. So because we cannot compute this exactly from the Hamiltonian dynamics, what we do is give an approximation. So suppose that the velocity was actually constant. If the velocity was constant, then you can exactly compute what this V0 twiddle has to be so that the end positions actually coincide after a time t. Okay. Of course, that's just an approximation, and you're going to have to pay the price of this approximation with the cost of control term. Okay, but that's exactly what we are doing here. So we are defining this V0 twiddle is exactly going to be the V0 plus the shift here. Okay, so this will be the V0 twiddle. And then you define a process P twiddle that gives the probability of the position starting from K0 twiddle with this shifted velocity. Okay. Right, so this is the P twiddle that we would need to obtain contractivity and smallness properties. And then you do the triangle inequality, and then this you estimate with the contraction. This is the cost of control term. So I'm trying to go over briefly. So in the end, this is the result that we obtain, is that if you consider a covariance matrix for the prior distribution and a potential function phi satisfying those conditions that I had before, then you can show that there exists an integration time capital T that is sufficiently small such that for any two initial measures mu1 and mu2, you obtain the spectral gap inequality for the Markov kernel associated to the infinite dimensional HMC algorithm. Where this rho twiddle is given is this distance in the phase space, again, weighted by the Lyapunov function. And then again, if you take mu2 in particular to be the invariant measure, which is posterior distribution in this case, then you obtain that for any initial point, or actually you could take this to be an initial distribution, you obtain this contraction of the iterations of the kernel towards the posterior measure in this Wasserstein distance. Okay, and actually we have this this upper bound more explicitly. I just put here that it converges to 0, but we have it more explicit. So essentially in this form with suitable constants C1 and C2. Okay, so this finishes the second application. So let me just put a conclusion here. So essentially what I did was to show you a general approach for showing rates of convergence towards a statistical equilibrium of systems that are subject to some kind of randomness. And the statistical equilibrium is essentially represented by the invariant measure of this random dynamical system. And then I showed two applications of this approach. The first one for approximating the invariant measure for 2D stochastic Navier-Stokes equations with a certain type of stochastic forcing term. And the second one, how to approximate the posterior measure in the context of inverse PDE problems by using the Bayesian approach. And one thing that I didn't say is that those conditions that I had in the potential function that guaranteed that we could obtain the spectral gap inequality, we verified in our paper that all of those conditions are satisfied in the application of the advection diffusion equation. Right? So in the context of trying to recover the incompressible velocity field from observations of the concentration of a passive scalar. So this proof that we obtained for the convergence of the infinite dimensional HMC algorithm in infinite dimensions gave us a different proof of this result that was open to for a very long time and only recently solved. And in the future, what we want to do is to extend this analysis that we've done for the HMC algorithm to the case of the numerical HMC algorithm. Because one thing that I didn't tell you is that when I constructed this Markov kernel, I should have emphasized we can only construct this if we know what the solution of the Hamiltonian dynamics is, right? Which is something that in only very simple cases you can give an analytical solution of. So in the more general case, of course, you would have to resort to a numerical approximation of the Hamiltonian dynamics. But then when you do this, you're going to introduce some numerical bias, which means that you're not going to, the dynamics of numerical specialization is not going to preserve the posterior measure as invariant. So you have to introduce a Metropolis-Hastings step to correct for this numerical bias. Okay, so that's what we want to analyze in the future, the more general case of numerical HMC method, and then obtain rates of convergence for this numerical HMC using the same kind of approach. So for that, we would have to understand in this infinite dimensional context, what does it mean? What does the Metropolis-Hastings step mean? Which is something that is usually just done in finite dimensions. So we have to, in order to work with these things in infinite dimensions, there are several generalizations that we have to do. And we have some preliminary results in this paper that is in archive as of last year. Okay, so with that, I'll finish here. And thank you very much.
Thank you. So any questions? Maybe I can start asking a question. So it's kind of related to what Jean-Luc just asked. So let's say if you have a system with a periodical forcing, just I'm thinking about some like geophysics system, you have annual circle or cycle, those things. So how do you deal with those kind of systems? So it exists kind of attractor, but it's not just equilibrium. It's like a time periodical equilibrium, roughly speaking. Yes.
Right. Yeah. No, I would need. Yeah. I don't know. I don't know if I'm understanding your question, but I think, I mean, all this approach relies on having a Lyapunov function. So it seems like from what you're saying, I don't know if you'll be able to derive a Lyapunov function in that context. I don't know. So what is that the forcing term that is sinusoidal?
It's kind of, yeah, exactly. Yeah.
Yeah, I don't know.
Okay.
I'll have to look at it more carefully, but.
Okay.
So could I follow up on that? I just, you had said something about that you need enough spatial scales in your forcing in the 2D problem. And I was wondering if you could just say a little bit more about what that really means and maybe give an example or somehow.
Right, well that, okay. So for the 2D stochastic Navier-Stokes case, to be honest, that the fact that we are considering this type of stochastic forcing term with where enough and large enough number of directions has to be forced is for simplicity. I mean, there's more advanced techniques that could be used for dealing with a degenerate type of stochastic forcing term where only a few number of spatial directions are forced. These are the hypoellipticity kind of techniques that were derived for studying Navier-Stokes equations by Martin Eyrer and company. So essentially, it's known for 2D Navier-Stokes equations that you can obtain your ergodicity just under a very degenerate stochastic forcing term. They say yes, you only have to force 4 Fourier modes, for example. But then you have to use more advanced techniques so that you were able to obtain a result like that, which we didn't use here. But it's I think that one could use these advanced techniques to improve this result. It's just that we didn't want to go through down that route. But yeah, I don't think that is something that cannot be improved here.
I see. Okay, thank you.
So any other questions? If no, let's thank Cecilia again. Yeah, thank you.
Thank you. Thanks for the invitation again.